last class we talked about arc length, didn't we? And we saw how arc length is really just, to find arc length, it's very similar to the way we've been finding area underneath the curve and the way we've been finding the volume of a solid when it's revolved around a certain axis, right? We use approximations, and these approximations in particular are approximations of portions of a curve and we use line segments to approximate those curves. And the idea is that when we take the limit of those little line segments, we get the whole curve. And the arc length formula of f from x equals a to x equals b is given by the integral from a to b of the square root of 1 plus f prime of x dx. And we saw last class how we derived this formula the way it looks like. And I think we didn't finish the arc length formula for the previous example. So then let's continuing from the continuing from last class. So our example was we have a curve y equals 1 plus 6x to the 3 halves. And I want to know how long that length is from 0 to 1. And let me just give you a visualization of this curve. So we have 1 plus 6 raised to the 3 halves. Sorry, this should be x. Whoa, what the? Hold on. X to the 3 halves. Great. Now my calculator is not working. Let me put it here. So I got 1 plus 6x to the 3 halves. So I just want to give you the visualization of this. So I have, this is my curve, you see? And I want to know what's the length of it from 0 to 1. So it looks like I just want to know hold on, let me see. I just want to know from 0 to 1, what is the length? What is this length here of this curve? That's what I want to figure out. You see that? I want to know what is this portion? What is this portion of my curve? How long is it if I were to draw it with a string or use a string to arrange it on top of that? How long of a string should I take? So then I can treat this as f of x, 1 plus 6x to the 3 halves. Then f prime of x will be 9x to the 1 half. That's f prime. Now I can use my formula. So I'm gonna write arc length as L. Arc length L is from 0 to 1, the square root of 1 plus 9x to the 1 half, because this is the derivative squared. Oh, I forgot to square this, sorry. This should be squared. So the arc length formula is this. And then this becomes, from the integral from 0 to 1, the square root of 1 plus 81x dx. And now I want to evaluate this. Now, how do we evaluate this integral? You guys are experts, right? At integrating. So how do we integrate this? Put it to the 1/2 power. Okay, that's one way we can start. We can write this as 0 to 1 of 1 plus 81x to the 1/2 power dx. Okay, and then what? Alexandra, you say u sub. What do we use sub? What kind of substitution are we going to make? U is going to equal to what? 1 plus 81x. That's right. I'm going to set this whole thing as 1 plus 81x, because then I can do what? Du dx is equal to 81. And then I can write this as du is equal to 81 over dx. I don't have an 81, but I do have a dx here. So I would solve for dx, and I get 1 over 81 du equals dx. So then this portion inside here is u, and this portion here would be negative. I mean, it would be 1 over 81 du. So then if I rewrite this, I would get a 1 over 81 on the outside of the integral. I would get the integral. Then I would have u raised to the 3/2 du. And then I have to change the bounds, don't I? So what are going to be the bounds, my new bounds? What are my new bounds? So if my first lower bound is 0 when x equals 0, what is going to be the corresponding u value if x equals 0? So if x equals 0, u will be what? 1. Perfect. And thank you, Samantha. You're already on top of it. So this is going to be 1. And then when x equals 1, u will be 82, because I just plug in the 1 into what u would be, right? So I get 1 plus 81, which is 82. So this would be my new integral. And I can now take the antiderivative. Oh, wait, Tosif, you're right. I jumped the gun. This should be 1/2. I jumped the gun. It's the antiderivative of u to the 1/2 would be u to the 3/2, and you have the 2/3 next to it, correct? And now I can evaluate my antiderivative at each of those respective bounds. So I get 82 raised to the 3/2 minus 2 times 2/3, 1 to the 3/2. And so then what is 82 raised to the 3/2? Does anybody know what 81 to the 3/2 power is? $729 or 3? Which one? Yeah, it's going to be a decimal. It's not going to be that clean of a number because 82 is not a square root. So you would be right, David, had it been 81. But it's actually a little bit it's not going to be as clean of a number. So yeah, these things are not going to be as clean. And one cubed. So actually, we're gonna want the exact value for this. So what is the exact value? So for now, I'm just gonna leave it as 2/3 square root of 82 cubed for now. This will be minus 2/3 because 1 to the 3/2 is just 1. And then I can take out the 2/3, so I'm left with 2 over 81 times 3. And I have the square root of 82 cubed minus 1. And so this would be 2 over 243. This would be the cube root of 82. Sorry, not the cube root. It would be the square root of 82 cubed minus 1. So that would be the exact value. And if you want the approximate value, plug that in your calculator, and what do you get? $6.10. So let me show you on Maple again. We use Maple. So they give you everything. So if my function, what's my function originally? The square root of 1 plus 81x. Sorry, no, my original function. We want the original function. It's 1 plus 6 times x raised to the 3 halves. And I'm evaluating it from 0 to 1. And then if I display it, I get exactly the function that I would get, right? The integral that I got, 0 to 1, square root of 81x. And then this is kind of similar to what we got. Of course, they don't have it factored. We have it factored completely. And the answer is indeed 6.103222891. Okay? So Maple can justify our calculations once again. So good. So this is exactly, or approximately 61022 dot dot dot. So far, so good. Straightforward. Okay. Let's look at another one. Um, what about find the arc length? Find the arc length of y equals x cubed over 3 plus 1 4x for my x values between 1 and 2. So what is this going to be? So this is my function, right? X cubed over 3 plus 1 over 4x. So then what's my derivative? I need to find my derivative first. I get what? X squared plus what? I get minus, right? I get minus 1 for x squared, correct? And so then I'm going to now find the arc length formula. So it's from 1 to 2 of the integral of 1 plus x squared minus 1 over 4x squared squared. And I get dx. Now what? Now I want to expand this. And so what do I get when I expand it? I get x to the fourth minus, what do I get? Minus a half? No, minus minus an eighth. Minus an eighth plus 1 over 16x to the fourth dx. And then I get some craziness here, don't I? I get x to the fourth plus 1 over 16 x to the fourth minus plus 7/8 dx. And that looks quite complicated, doesn't it? Is there a way we can integrate this cleanly? Yeah. It doesn't look like there's a specific u sub we can do. And yeah, so for this, I think we may have to be relegated to use, oh, wait a minute. I think I miss. I got it. I got that. That's right. Yeah, so there's at the moment, I don't think we have any of our integration techniques that work. We don't have a u sub here that we can do. We don't have a um, wait a minute. Yeah, I don't think any u sub works here. And there's no trig that we can apply here. So that's quite interesting. That's interesting. So can anyone think of something here to like get the ball rolling here? Because at the moment there is nothing that can be done so far from my vantage point. X to the negative one. Yeah, I don't think there's anything we can do at the moment. It's an interesting integral. That just didn't usually. So with arc length formulas, usually the integral that you get is something that you can work with. But this one here is a bit more complicated than I had anticipated. So you know what? Let's just keep that there for now. We'll come back to it. Um, we'll come back to it. So I'll give you another one, and hopefully this one works out a little bit cleaner than this previous example. So what if I want to find the arc length? I'm sure it will, but we'll come back at 143. Yeah. So in math 143, we'll come back to that most likely, right? That's strange. That's a weird integral. Anyways, so what if y is instead? What if y squared is this? 4x plus 4 cubed, and my interval is from 0 to 2. And they also say y is bigger than 0. So this one already is going to have a more of a nicer form than the other one. So right now we have y squared. So the first thing we have to do, right, is find y by itself. So we take the square root on both sides. And so then I can take the square root of 4, which is 2. So this really is 2. And then the square root of x plus 4 cubed, I can rewrite this as 2 times x plus 4 to the 3 halves. So this is really what y is. So all in agreement? Thank you, Tassif. Yeah. So I was also looking at it. I was like, wait a minute. That's a I anticipated this example being much simpler, but it looks like it's not. But I'm still gonna look over this because apparently it should be simple. It should be you should be able to find the antiderivative of it, apparently. But from just a glance at it, right? Just at a glance. Sorry about that. I don't know who'd be calling me right now. But just at a glance, there's nothing we really could do at the moment. But regardless, but thank you, Tasa, for looking into that integral. Yeah, apparently it's one of those examples that you should be able to, but I don't see it. I don't see it. But anyways, but this one will work out because there's something nice about this being raised to three halves. I hope. And then what? What is the derivative? So this is f of x, right? So what's my derivative then? My derivative, I do the power rule, and I get 3x plus 4, right? Raised to the 1/2 power. So you see, most of the time when we have derivatives or functions that have fractional exponents like this, it's nice because it works out with the arc length formula. So the arc length formula is what? 0 to 2, square root of 1 plus, then I have my derivative, 3x plus 4 to the 1/2 power, and this whole entire thing is being squared. And this is dx, of course. And so then when we do this, we get 0 to 2 of the square root of 1 plus 9 parentheses x plus 4, because the 1/2 in the square goes bye-bye. And then I get this, 0 to 2, the integral of 1 plus 9x plus 36 dx from 0 to 2. And this is the square root of 9x plus 37 dx. So then how do I evaluate? This is a lot simpler than this guy over here. A lot simpler. So most of the time when you have integrals of square root expressions, they're not that simple. They really aren't. They're kind of complicated. I may have expanded incorrectly above. Possibly. I think you're right. I think you're right. So we'll see if we can come back to that. I think you're right, David. I expanded this incorrectly. I don't think there should be a 1/8. I think this inside here should be um, half. And you get 9 over 16. Yeah, I think the middle term should be, it should not be a -8. It should be um, a half. But like I said, we'll see if we can come back to that. But something's got to give there, right? Okay, and then what? How do we evaluate this integral here? So it's very similar to the one we did in the first example. Yep. For these kind of problems, whenever we have a linear expression underneath the square root, it's just natural to be like, oh, we can say u sub. And what do we u sub? We u sub everything that's underneath the square root. So I get 9x plus 37. This becomes du over dx. This equals 9, which means that du over 9 equals dx. Then I can integrate, and I got this 1/9 that pops out, the integral of the square root of u du. And then what does the new integration bounds become? What do the new integration bounds become? So when x equals 0, my y value is 37. And when x equals 2, my y value is what? 55. Great. Because I'm adding by 18. So then I got two of these new bounds, 37 and 55. And then the square root of u can be rewritten as u to the 1/2 power, which is easier, so I can find the antiderivative of this. And the antiderivative is 3/2, 2/3 thing again, right? Evaluated from 55 to 37. And this becomes 1/9 of 2/3 times the square root of 55 raised to the 3rd power minus 2/3 the square root of 37 to the 3rd power. And you can take out the 2/3. So if I take out the 2/3, I'll get 2/27. The square root of 55 cubed minus the square root of 37 cubed. And this would be the exact form. And if I were to find the sorry about that. I can't open this. There we go. So here we have 2/27 being multiplied by, let me just write it as a fractional exponent. So I raise this to the 3/2, and then I subtract it from 37 raised to the 3/2. And I get 13.5428, so on and so forth. And just to make sure, I'm going to share my screen with Maple. And so Maple, I'm going to give it the original function, but I can't have a y squared, so I'm going to use the square root version. So the square root of 4 multiplied by x plus 4 raised to the 3rd power. And this is from 0 to 2. When I display it, I get exactly the integral that I got originally, and I got something similar to that effect, but we have it in the factored form, and we get the same thing, right? 5.4286660. So it's all good. It's all good. 5.4228. That's right. Okay. So far, so good. Okay, so let's go back to the problem that we were having with the other one. And there's something that I think I have messed up with. I think you're right. So if I take this portion here, right? So I think this is where I think I went a little too fast. So x squared minus 1/4 x squared. If I square this is the same thing as saying x squared minus 1/4 x squared multiplied by x squared minus 1/4 x squared. So when I square it, I get x to the 4th, then I get minus a 4th, then I get minus a 4th, then I get plus 1/16x squared. And then I get x to the 4th minus a half plus 1/16x squared. And if I put this inside, so this inside here should be a 1/2 instead. And then this should be a plus a half, right? Because 1 minus a half is plus a half. So that's what I get. But does this help me? Yes, you're right. Wait, what is negative x to the fourth over 4? This should be, pardon me, this should be to the fourth power here, right? David, how did you get the negative x to the fourth over 4? The thing is, you multiply, right? You multiply the first with the last and the inner terms, right? And when you multiply them, because they're x squareds, they cancel out. So you see that? So you don't get, yeah. Don't worry, David. We all mess up. We can catch it. But then after this, can we do anything here? Is it possible? So maybe. Let's look at this. So this is x to the fourth plus 1 over 16 x to the fourth plus 1 half. It might help if we set everything to the same denominator. So if I do that, I would get what? I just have to multiply this by 16 x to the fourth over. Actually, no. This would be x to the eighth over 16. Pardon me. So if I want this to be, yeah. So this would be 16 x to the eighth over 16 x to the fourth plus 1 over 16 x to the fourth plus this is 8 x to the fourth over x 16 x to the fourth. So I made them all the same denominator. And then I can write this as 16 x to the eighth plus 8 x to the fourth plus 1 all over 16 x to the fourth. And then this is actually a perfect square trinomial. And then I can factor this as 4x to the fourth plus 1. And this will be over squared over 16x to the fourth. Oh my goodness. This is doable. It's just that it's a lot of algebra. Does everybody see what I did? I I looked at the interior of my square root, and then all I did was I wrote it as a single fraction. And I noticed that this is a perfect square trinomial. So again, your algebra skills has to be on point for this. And then I can replace this. I can replace this as 1 to 2 of the square root of 4x to the fourth plus 1. This is squared divided by 16x to the fourth dx. But then I take the square root of the numerator and denominator. So the numerator becomes 4x to the fourth plus 1 divided by the square root of 16x to the fourth is 4x squared. Are you guys with me? Are you guys following what I'm doing? It's a little crazy. Okay, and now how do I evaluate this? So the hard part was done for you guys. Now how do you evaluate this? How do you integrate this? So there's no room here, so I'm gonna put this over here. Let me just copy this. Anybody know how to integrate this? Do we need U sub? Nope. That's right. No U sub here. We don't need U sub. That's right. We rewrite it. How do we rewrite it? The only thing we can do to rewrite it is to separate as two fractions again. So if I separate it as two fractions instead, isn't this a lot doable? Because what's nice about it is you can simplify, right? And then when I simplify this, the first fraction, I get x squared. Oh, that's pretty easy to integrate. Pardon me. And then this becomes 1/4 x to the negative 2. Very, very simple functions to integrate. So I get x cubed over 3. And then when I integrate this, I get what? I get minus, right? Minus 1 over, this becomes 1 over 12 x cubed. All in agreement? And then I evaluate this from 2 to 1. So when I do that, I get 2 cubed over 3 minus 1 over 12 times 2 cubed minus parentheses 1/3 minus 1 over 12. So this is 8 over 3 minus 1 over 12 times 8 is 96 minus a third plus a 12th. This fraction is kind of weird. And so then this becomes what? If I want to make them all the same denominators, make them all 96. So this is 96. So 96, 3 goes into 96 32 times. So this is 32. So in order, I can't, wait, can I? Yeah, I would have to multiply this by 32. So this becomes 32 over 96 plus, then 12 goes into 96 8 times. So this is 8 over 96. And then I do the same thing again, right? 32, when this, and instead this would be 32 times 8 over 96. And then 8 times 6 is 16. This becomes 256 over 96 minus 1 over 96 minus 32 over 96 plus 8 over 96. So what does this become? 256 minus 1 is 255. 255 minus 32 is what? 223? No, 224. And I add that by 8, 96. And I get a whopping 232 over 96. And can I cancel this further? 232 over 96. If I divide it by 2, I get, what do I get? I get 48. And if I divide 232 by 2, I get what? 176. And can I break this down even further? I can. I can divide it by 2 again. And what do I get? Can I divide this further? I can divide this by 4. So if I divide this by 4, I got this as 12. And then I get what? 64 by 12. No, that's not right. By 4, pardon me, by 4. 16. Yeah, 64, right? So I'm getting different numbers here. I get 29 over 12, 116 over 48, and 44. So wait, what is it? Which one is it? 44 over 12? That's right. Pardon me. It's not 64. It's 44. 44 over 12. And I think I can reduce this further, can I? By 4, I get what? Is it 11 thirds? Is this the final answer you guys get? Well, we can just check it. So 11 thirds, just to make sure, is 3.6, right? And then what if I get 8 thirds minus 1 over 96 minus 1 third plus 1 over 12? We get 77 over 32. So what happened? There we go. Thank you, Justin. Justin's on the money. So yeah, 132, 232 divided by 176 should be what then? I can't divide by 2, apparently. 116? That is right. I can't believe I said this is 170. I was thinking about something else. I was thinking about completely something else. So this is 116. So then it should be a lot better. So then after that, we could divide this by 4 again, or we could divide this by something bigger, probably 4, right? Divide this by 12. So if you divide this 116 by 4, I get what? I get or maybe something's wrong with the actual 232. Maybe it shouldn't be 232, right? Let me just see. So I think something's wrong with. Let me just see. Yeah, 256. So 256 minus 1 minus 32 plus 8. So yeah, there's a little mistake here. It's 231, guys. You see that? There's little tiny mistakes like this that get you. So this should be not 224, not 224, but this should be 231, 223. So when I subtract, oh, I see what I did. 256 minus 1 is 255, minus 32 is 223, plus 8 is 231. Now we're talking. And then you can divide. Then you should be able to divide this. So 231, pardon me. 231 divided by 96 is that number, which I think reduces to 77 over 32, if I'm not mistaken. So if I want to check this out, 77 divided by 32 is exactly the same thing. So you divide this by 3. You can divide this by 3. Yeah. Yeah, you can divide both by 3. And so then you get 77 over 32. So I know, guys, I know I could do this with my calculator, and I know everything is like computationally, like we can just do this. But I want, because sometimes I see it on your exams, like you guys get the answers, but then there's no clear cut thread. There's no like pathway to your final answer, and it's better for me as well. When I look at your work, I'm like, oh, I'm able to see, and even for you, for your own good, right? You're able to see where you go wrong. And let's just check. Let's just check with Maple, since Maple has a built-in engine for this stuff. So let's see what happens if I put my original function, which was what? What's my original function? It's x cubed divided by 3 plus 1 over parentheses 4 times x. So you have to be very specific the way you write it for this, for Maple, for 1 to 2. So let's see what it says. We get something very similar. This is 2.45, and what do we get? We get like 2.40625. So is there something that we didn't account for? It's okay. It's okay. This is fine. This is the way life is. Sometimes you run into little things. So, is there something that, so as you can tell, right? As you can tell, the integral that we get is exactly what the one we get. It's the same thing. So there's something that there's a tiny little thing that we must have missed. Oh yes. Yes. I see exactly where. Do you guys see it? Look back. So up until this point, guys, it's all good. Up until this point here, up until this point here, up until this point here, we're good. Then this next step here, no good. No good. And that's on me, not on you. So do you guys see the integral here? Antiderivative? That's fine. But what's the antiderivative of this? Do you guys see it? This is a typical mistake people do sometimes. So actually, this is not the antiderivative. 1 over 12 x cubed is not the antiderivative. That would be actually the derivative in a sense. But what's the actual antiderivative of 1/4 x to the 1/2 to the 1 to the negative second power, negative 2 power? It should be what instead? That's right. That's right. Because we're adding 1 to negative 2, which is negative 1, and we're dividing that by negative 1. So the answer should actually be 1 over 4 to the x. That's what it should be. You see that? A little mistake there. That does a whole cascading effect. And so then this becomes not this. This becomes what? 1 over 8. So I think actually our computation will be a lot simpler. And this will be 1/4. And this will be plus 1/4. And this should be 1/8. So now this is what I have. So actually this whole thing, no good. Does everybody follow that? And then the least common multiple should be 24. So I multiply um, by 8 and I get 64 over 24 minus 3 over 24 minus 8 over 24 plus 6 over 24. And then I do 64 minus 8. That becomes 61 minus 8 plus 6 over 24. 61 minus 8 is 53. 53 plus 6 over 24 should be what? 59 over 24. And is this the correct one? 59 over 24. That's exactly right. So this is exactly what Maple gets. 2.5483 repeated. Does everyone see that? So be very careful. Be very careful of the antiderivatives. And guys, this is okay. Like it's like a dilemma, right? Um, teaching mathematics, because if I were to teach it to you guys where I make no mistakes, then you would think that mathematics, the act of doing mathematics is doing no mistakes. But then when you're actually in the line of work and you actually do mathematics, mistakes happened all the time. So I feel like sometimes the way mathematics is presented in the classrooms, in particularly, is a bit misleading. I would say it's a lot misleading because you have the idea that the person in front of the room or in front of the board or teaching whatever is infallible in a way because they should know exactly what everything how things are going to happen and all that. But then if you're true to yourself, if you're really honest with yourself, the person in front, they know that, you know, we're quite limited in the scope of our knowledge as well. And that's actually part of the activity of doing mathematics, is knowing how to mess up, but at the same time, not that you know how to mess up, is that you learn how to bounce from your little mistakes that you may do. So always when you do something right, you always want to um, make sure that every step is right. And sometimes we look over things and glance over things, as we do, right, in our exams and our quizzes, right. So that's why it's good to look over whatever you do. Don't always think that, oh, I did this correct. Make sure you really pay attention to every detail. And so there's a lot of, auto analysis, of reevaluation of what you do. That's just what I want to say, because sometimes people, I've had that idea that, oh, everybody that teaches mathematics, they know everything. They don't know. They don't. And that's just the nature of it. But anyways, is this clear now? Do you guys see how we were able to evaluate this integral? This is not an easy integral, and it's not because we don't know how to integrate. Well, we don't know how to integrate this portion here. That's not the difficulty. What was the difficulty? The difficulty was that we had this expression originally, right? That's the difficulty, guys. You're like looking at this, you're like, nah, I can't do this. I can't integrate this. But then if you're a little patient with yourself, just be a little patient and be like, wait a minute, what if I were able to express this as a single fraction? And it just so happens that if I were to do that, look what happens. I get an expression that's very nice. Why is it nice? Because one of the things is it's squared, so it's a perfect square. I can take the square root of that, and the denominator is also a perfect square. Beautiful. So then once I'm able to take the square root of those perfect squares, that takes care of the square root. I don't have to worry about the square root. Usually the square root makes everything more complicated. But in this case, I'm able to get rid of the square root. And then from here, I'm able to move on. So a lot of the times, right, I told you guys, when you find integrals of functions, it's the algebra portion that gets hard. It's not necessarily the actual finding the antiderivative of the anti-differentiation step is not the hard part. It's getting to that anti-differentiation step that's the hard part. And a lot of that is algebra manipulations, u sub, or squaring things out and combining things and separating things. So you have to work all this at the same time. That's what makes integrating difficult, but also very challenging and actually pretty fun. It could get really fun. Okay, so does everybody understand arc length? How to use the formula? It's just the integral from a to b of 1 plus the derivative squared. Okay? Okay. Now one last thing. There's some problems on your homework that are a little different than the solids of revolution topic that we have discussed. And I want to just touch upon that a bit. And then we can call it a semester. Well, after you take the last quiz, which shouldn't be too bad. I hope not. Okay, so if I look at the so we're gonna make a little mini detour back into volumes. So if you look at like questions 15 through 17, 18, not through 19, through 20. So let's look at the first one here. So for number 15, I'm just going to give you how to do one of them. Number 15 on your homework number number 11. We have a volume, right? It says a volume is described, find the volume of the described solid S. It says the base of S, the base of the solid is a circular disk, is a circular disk with radius 4r. And you said, and it says that we have parallel cross sections perpendicular perpendicular to the base are squares. Okay, so this requires a visualization of this. And it's not easy at first. So the base of S is a circular disc, right? So I'm gonna draw a circular disc. And what do I know about the circular disc? The radius is what? The radius is 4r, correct? Now, what is it saying? This solid that I have, this is my base. This is the base. But then the solid is more than just the base, right? It says that if I draw parallel cross sections, so if the cross sections that I create, the parallel ones, they're perpendicular to the base. So the base here is this. So we have this kind of thing happening. So this is one cross section. It says that these cross sections here, I don't know if you can see what I'm trying to draw here. These kind of cross sections here. So this here, this is a square. And as you move along the circle, the squares get bigger as the radius gets bigger, and it gets smaller as the radius gets smaller. Do you guys see that? Let me see if do you guys understand what I'm saying or no? Yes? Oh, okay. So the idea is that I'm stacking squares. That's the idea. I'm stacking squares of different sizes depending upon the circle base that I'm at. So these are this is one of the squares, but I have smaller squares as I get closer to the edges. So the idea is, how do I find the volume of that particular how do I find the volume of that solid? So then what we tend to do is to create a coordinate axis for the base. So I say uh, this is x, right? And this is my y. And the radius is 4r. So that means that my big radius, the radius of this guy here is 4r. Okay? It's 4r. Now, how do I find if I know the cross sections of this volume, how do you find the volume? So the volume of any solid, if I know each cross section, is given by this formula from a to b, the function a of x dx. And remember, a of x represents the area of cross sections. So remember when we talked about the disk method, the area function is the area of the circle, pi r squared, or we also have the cylindrical part, which is the h, but that h, that change in x becomes the dx. So this is the big picture behind the disk method behind the washer method. It's really to find a volume, you have to find the integral of the cross section. So if I know every cross section, then I just have to integrate it from A to B. So then what is the cross section that I have here? What is my cross section? My cross sections are squares. So then what would be the area of one square? How do you find the area of this one square? Well, I would have to know what? I would have to know the side of one of the squares, right? If I know the side, then I know everything. I know the area. So what's the side of one of the squares? So maybe I may have lost you guys with this. But so the idea, guys, is that we're gonna write the equation of the circle. What's the equation of a circle with radius 4r? What's the equation of the circle? So let's just do this real quick. Equation of circle. It's gonna be what? X squared plus y squared equals the radius squared, right? We should know this formula. So this is 4r squared. So this becomes x squared plus y squared equals 16r squared, correct? So then what does that tell me? That tells me that y squared is 16r squared minus x squared, which means that y is equal to the square root of 16r squared minus x squared. But then what is that? That's the y value here, right? So if you look at this portion, half of the side of one square is equal to y. Y is equal to half side of square. But I need to know one side of the square. So what's the full side of the square going to be? It's going to be 2y. So 2y equals the side of one square. But then what is y equal to? Y is equal to this expression of x. So really the cross-sectional area with respect to x is going to be 2 square root of 16r squared minus x squared. And this is the hardest part to get, is to figure out what in the world is the cross-sectional area for one of those cross-sections with respect to x. And then I know what? What do I know about the x values here? One is going to be 4r and the other one is going to be negative 4r, because that's exactly what the radius is. The radius of my circular disc is 4r. So I go as far as 4r to the right and as far as negative 4r to the left. So what's going to be my integral? My volume is going to be the integral from negative 4r to positive 4r of what? The cross-sectional area is going to be what? Oh, pardon me. The cross-sectional area is this squared, because the area of a square is side squared. So I know one side, I just have to square it, right? I have one side of the square. Now I square it. And when I square it, I get 4 times 16r squared minus x squared dx. And then from here, I can integrate 4 times, let me just write this out. This becomes 64r squared minus 4x squared dx. And because this is an even function, I can write this as 0 to 4r and just multiply it by 2. And then the antiderivative is 64r squared x minus 4x cubed over 3, evaluated from 0 to 4r. And this whole thing is being multiplied by 2. This is 2 times 64r squared times 4r minus 4 times 4r cubed over 3. This is 2 times 64 times 4 is 256 r cubed minus 4 times 64 r cubed over 3. So this is 256 r cubed minus 256 r cubed over 3. And this is multiplied by 2. And then what do I get? I get 256 multiplied by 3. That's 768. So 768 r cubed over 3 minus 256 r cubed over 3. And this is minus 256 is 512. So this is 2 times 512 r cubed over 3, which the result will be 1024 r cubed over 3. So this question is a bit more geometric in nature, but the general idea, the big idea, guys, the big idea is that to find the volume of a solid, if I were to know every cross section, and because every cross section here are squares, then I know that if I know one side, then I know how to find the area of that whole cross section. And if I can do that for every single possible x value within these bounds of integration, then I would be able to find the volume of the entire solid. So just to give you a visualization of this, because this might need more visualization, this is the solid that I want. So this is my base here. This is my base. And if I were to draw all possible cross sections that are squares, right, I would get this kind of shape. It's kind of a strange shape to look at. And I can't replicate it on Maple. I don't know how to do that. I don't think they have that function, apparently. But think about having very thin squares, and as you move along the x-axis, right, the squares get bigger and bigger. So then, and then as you approach from one end of the circle to the other end of the circle, the squares get small, big, 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 big as possible. Then they slow down again. They get to smaller and smaller. And that forms this weird solid. But because this solid, if I were to cut it perpendicularly to the base this way, it always forms a square as my cross section. Then I can find the volume of this solid. Okay. Does that make more sense now with the visualization? Guys, this stuff is really just tying with what we did with the disk. It's really just that kind of idea. Okay, guys. Yeah, it does look weird. It's a strange shape. It's a strange shape. But the important thing, guys, the important thing is that we know the cross section for that solid. So if we know the cross section of each solid, if we know the area of the cross section that we create, we can always find the volume by this method, by this formula. So the volume of a solid is given by the integral of the cross-sectional areas. That's really the main idea. Alrighty, guys. So congrats. You made it. Made it to the end. We've all made it to the end. It's been a crazy semester. I hope you guys enjoyed portions of this class. I know that this kind of setup is not the greatest. It's not the best from both ends. I don't think it'll be much better to have seen you all in person, and we can communicate a lot better, have a better feel for each other that way. But we did what we could in the climate that we're in. So you have your next final and final quiz. You don't have to do this ever again. Aren't you happy? So I'm gonna post it. I'm gonna post it on Google Classroom as we speak. You have 20 minutes. I'll keep the final quiz, huh? So let's see. It should be. Let me just see. It should be up now. Quiz number 6. So on Google Classroom, it should be up. It's only 4 questions. You got 20 minutes. And you may begin. All right, guys, you have 5 minutes left.
Have a good day.
Have a good day.